In 1843, sailors navigating the southern hemisphere noticed something strange happening in the night sky. A star that had existed quietly for thousands of years suddenly brightened until it became the second brightest star visible from Earth. Only Sirius appeared brighter, and Sirius is roughly 1,000 times closer. Astronomers at the time had no explanation for what they were seeing. No known type of star was supposed to behave this way. The eruption released more energy than our sun will produce across its entire lifetime, and then the star survived. That single fact is the reason astronomers still monitor Eta Carinae continuously today. The system sits approximately 7,500 light years away inside the Carina Nebula, and it is one of the most massive star systems close enough for humanity to study in real detail. The primary star alone is estimated to contain more than 100 times the mass of the Sun. Stars that massive are not supposed to remain stable for long. Eta Carinae has already erupted multiple times in recorded history. Surrounding the system is a gigantic expanding cloud of gas and dust created by previous eruptions, evidence that the star has been tearing pieces of itself apart for centuries. And right now, astronomers are watching it brighten again. NASA, Hubble, Chandra, and ground based observatories across Earth have spent decades tracking changes in the system because when Eta Carinae finally dies, it may produce one of the most violent stellar explosions ever observed by human beings. There is another detail that makes the situation even stranger. Everything we know about Eta Carinae is already 7,500 years out of date. The light reaching Earth tonight left the system when humans were still building the earliest civilizations. Whatever is happening there right now is completely unknown to us. The star could already be dead. This channel grows because of people who take a moment to subscribe and support videos like these. If that's you, thank you. It genuinely helps. The story begins with a star that became too bright to ignore. Imagine placing our sun beside Eta Carinae and reducing both stars to a single number. Not brightness, not temperature, mass. Everything begins there. Our sun contains one solar mass, the standard unit astronomers use when comparing stars. It is calm, balanced, and patient. Deep in its core, hydrogen atoms fuse into helium at a controlled rate, releasing energy slowly enough to sustain the star for roughly 10 billion years. Nearly half that lifetime has already passed, yet the sun remains remarkably stable. Day after day, century after century, almost nothing changes. But mass alters the rules with brutal speed. A star with 10 solar masses does not simply become 10 times brighter. Its gravity crushes the core harder, raising pressure and temperature until fusion accelerates violently. The star burns hotter, shines blue instead of yellow, and consumes its nuclear fuel in tens of millions of years rather than billions. Scale upward again, toward 100 solar masses, and stellar physics enters dangerous territory. The equations still function, mostly, but stability begins slipping away. Eta Carinae sits inside the Carina Nebula, approximately 7,500 light years from Earth. What appears from a distance as a single brilliant object is actually a binary system, meaning two stars orbiting one another. The larger member, Eta Carinae A, carries an estimated mass between 100 and 120 suns. Its companion, Eta Carinae B, likely holds between 30 and 60 solar masses. In almost any other region of the galaxy, Eta Carinae B would dominate attention. Here, it disappears into the shadow of something even more extreme. Massive stars do not age gracefully. They burn through their fuel with astonishing wastefulness. Eta Carinae is only around 2 to 3 million years old, younger than some mountain ranges on Earth, yet it is already approaching the final stages of stellar evolution. Compared to the Sun, its lifespan is not 100 times shorter, it is closer to 3,000 times shorter. The star is effectively sprinting toward destruction, and there is another layer to hold in your mind as we continue. The light reaching us tonight began its journey 7,500 years ago, when humans were building the first cities from mud brick beside young rivers. Everything we see from Eta Carinae belongs to that distant past. The Carina Nebula surrounding it remains one of the Milky Way's largest stellar nurseries, a vast cloud where new stars ignite beneath the radiation of a giant already beginning to fail. That tension defines everything here, a region filled with birth, illuminated by something dying, because eventually gravity wins. It always does. The real question is how long a star this massive can resist itself before the balance collapses entirely. And from 7,500 light years away, what would that collapse actually look like when the struggle finally ends? Logs from 19th century ships rarely sound dramatic. Coordinates, weather conditions, sail damage, currents. But during April of 1843, navigators crossing southern oceans began noting something unusual above them. A star they did not recognize had become impossible to ignore. It appeared in the constellation Carina, low in the southern sky. Only months earlier, it had been unremarkable. Then the brightness surged. Within weeks, Eta Carinae became the second brightest star visible from Earth. Only Sirius appeared brighter, despite Sirius being roughly 1,000 times closer to us. Sailors started using Eta Carinae for navigation because it stood out so clearly against the darkness. A distant stellar system, buried deep inside a nebula, had suddenly transformed into one of the dominant lights of the night sky. No one understood why. The 19th century possessed no framework for an event like this. Supernovae were poorly understood even in principle, and Eta Carinae did something stranger still. It erupted with extraordinary violence, releasing more energy than many stars generate across their entire lifetimes. Yet the star itself remained alive afterward. That contradiction still defines the mystery. Over a span of years, the system expelled somewhere between 10 and 40 solar masses of material into surrounding space. Entire suns worth of matter were hurled outward at hundreds of kilometers per second. The eruption did not arrive as a single flash. It unfolded gradually, climbing in brightness, lingering near its peak, then fading with frustrating slowness. Astronomers kept watching because they had nothing else to do. At observatories in Cape Town, Cordoba, and Parramatta, careful measurements accumulated night after night. Positions were recorded, magnitudes compared, notes preserved. Even without theoretical explanations, observers understood they were witnessing something unprecedented. The sky itself had changed during a human lifetime. But the strangest part came afterward. A normal supernova destroys the star responsible for it. The core collapses, the outer layers disperse, and only a remnant remains. Eta Carinae ignored that pattern completely. After ejecting a catastrophic amount of mass and energy, the system survived. The central star endured behind the expanding debris. More than a century later, astronomers finally created a category for eruptions like this. They called them supernova imposters, events that mimic the violence of stellar death without completing it. The name emerged because Eta Carinae forced it into existence. By the early 20th century, the star had faded so dramatically that it vanished from naked eye visibility altogether. Imagine watching the second brightest star in the sky slowly disappear within a single lifetime. Future generations reading old observations struggled to believe the reports were accurate, that the records matched across continents. The eruption had been real, and even now it remains the largest non terminal stellar eruption ever directly observed by human beings. We still do not fully understand what mechanism inside the star released that much energy without tearing the system apart completely. Eta Carinae survived its own catastrophe, then continued evolving as though the event had only been one phase in a much longer process. If you aim a powerful telescope toward Eta Carinae today, you do not immediately see the star itself. You see debris. A vast cloud surrounds the system, glowing softly in reflected starlight and expanding outward through the Carina Nebula. This structure is called the Homunculus Nebula. The name comes from Latin, meaning little man, because early telescopic sketches showed two rounded lobes separated by a narrow waist, vaguely resembling a human figure suspended in space. The shape is strange, almost anatomical. What we are looking at is the preserved aftermath of the 1843 eruption, matter thrown outward so violently that it never fully dispersed into the surrounding galaxy. Instead, it wrapped around the star in a dense shell of gas and dust that continues expanding even now at roughly 650 kilometers per second. The nebula has already reached a diameter of approximately 1.4 light years, and it is still growing. Visible light struggles to penetrate the material. Dust grains inside the homunculus absorb and scatter shorter wavelengths so effectively that the central stars became partially hidden behind the wreckage they created. For decades, astronomers could study only the surrounding cloud, while the core remained obscured. But the launch of the Hubble Space Telescope in 1990 changed that relationship almost immediately. Hubble carried ultraviolet instruments capable of penetrating portions of the dust veil. Ultraviolet light consists of shorter, more energetic wavelengths than visible light, allowing astronomers to isolate structures hidden within thicker regions of gas. Eta Carinae quickly became one of Hubble's highest priority targets because, for the first time, researchers could begin observing the surviving star directly through the expanding debris field. What they found deepened the mystery. The homunculus is not remotely symmetrical. A normal explosion in open space tends to expand outward in all directions equally, forming something close to a sphere. Eta Carinae produced two giant opposing lobes, separated by a dense equatorial disk, meaning the eruption expelled far more material along some directions than others. Something shaped the blast while it happened. Several explanations compete for attention. The companion star may have distorted the eruption gravitationally during close orbital interaction. Rapid rotation in Eta Carinae A could also have concentrated material toward the poles, while magnetic field asymmetries may have redirected energy unevenly through the outer layers. None of these models fully explains the geometry we observe. Inside the main lobes, astronomers discovered an even faster outer shell moving at nearly 3,200 kilometers per second. That speed suggests a second ejection event layered over the first, as though the eruption unfolded in multiple stages rather than one continuous outflow. The total expelled mass remains staggering, somewhere between 10 and 40 times the mass of our Sun, launched into surrounding space within only a few years. And because the homunculus is close enough to map in detail, it has become something extraordinarily valuable. We are not merely observing a nebula, we are examining a preserved three-dimensional record of what a near supernova eruption actually looks like from the inside, frozen in expanding gas before the evidence could fade. In the 1920s, British astrophysicist Arthur Eddington began asking a deceptively simple question: how bright can a star become before light itself tears the star apart? The answer became one of the foundations of stellar physics. Inside every star, two forces compete constantly. Gravity pulls inward, compressing gas toward the core. Radiation pushes outward, generated by nuclear fusion deep inside the star's interior. Radiation pressure means light carrying momentum, exerting force as it escapes through matter. Most stars exist in balance between these opposing pressures. Eddington calculated the theoretical upper boundary where that balance fails. Today we call it the Eddington limit. At that threshold, outward radiation exactly equals inward gravity. Any increase in luminosity should destabilize the star, driving material away from the surface in powerful outflows. Cross the limit too dramatically, and the star should begin destroying itself faster than gravity can hold it together. For ordinary stars, the rule works remarkably well, but Eta Carinae does not behave like an ordinary star. Its luminosity is estimated at roughly 5 million times greater than the Sun's. In practical terms, the system radiates more energy in a single second than our Sun emits across approximately 50 days. The outward pressure generated by that luminosity should be catastrophic, yet the star remains intact, not stable, but intact. By conventional expectations, Eta Carinae should have dispersed itself long before the 19th century eruption ever occurred. The fact that it survived afterward only deepened the contradiction. Astronomers were no longer dealing with a star that merely approached theoretical boundaries. They were observing one that appeared to violate them continuously. That realization forced theorists into increasingly complicated explanations. One possibility involves convection, the large-scale circulation of hot gas inside the star. Convective instabilities may redistribute energy unevenly, preventing radiation pressure from concentrating strongly enough to fully disrupt the outer layers. Another proposal focuses on turbulence, chaotic motion in the stellar atmosphere that reduces opacity, meaning the gas becomes more transparent to escaping radiation. Then there is porosity. In stellar physics, porosity describes an atmosphere filled with lower density gaps through which radiation can escape more easily. Instead of pushing uniformly against the entire surface, light leaks outward through thinner regions, easing pressure in other areas. The star effectively vents energy through weak points. But none of these models completely accounts for what we observe. Eta Carinae still shines too intensely. It still loses mass too violently. It still survives longer than simplified equations suggest it should. This is why astronomers classify it as a luminous blue variable. The name sounds descriptive, but it is really an admission of uncertainty. These stars are defined less by a precise internal structure than by their behavior. They brighten unpredictably, erupt episodically, and fluctuate on timescales that stable stars never display. Eta Carinae sits at the extreme edge of that category. What makes the system unsettling is not merely its size or brightness. It is the fact that one of our most trusted theoretical limits appears insufficient in its presence. Out there in the Carina Nebula, hidden behind expanding debris, a star continues operating in conditions that physics struggles to describe cleanly, as though nature itself has found loopholes in rules we once believed were absolute. Most of the time, when we picture a star system, we imagine a single sun hanging alone in darkness. Eta Carinae does not grant us that simplicity. There are two stars here. They orbit one another inside the dust and gas of the homunculus, locked together by gravity in one of the most violent binary systems ever studied. The brighter primary dominates every image and headline, but the companion star shapes nearly everything happening around it. Astronomers call it Eta Carinae b. Even by galactic standards, it is enormous. Estimates place its mass somewhere between 30 and 60 times that of our Sunday. A star like that would normally stand among the most luminous objects in the Milky Way. But beside Eta Carinae, it becomes strangely difficult to notice, buried beneath glare, radiation, and expanding debris. The two stars circle each other every 5.54 years. Their orbit is not circular. It forms a stretched ellipse, meaning the distance between them changes dramatically across each cycle. At a pastron, the point where they are furthest apart, the separation roughly matches the distance between the Sun and Saturn. Then gravity pulls them back together. At periastron, their closest approach, the stars pass within a distance comparable to the gap between Earth and Mars. Two unstable giants sweep past one another at extraordinary speed, each carrying intense stellar winds into the encounter. A stellar wind is a continuous outflow of charged particles escaping from a star's surface. Our Sun produces one constantly, shaping the entire solar system. But Eta Carinae's winds are vastly more powerful. Material streams outward at millions of kilometers per hour, carrying enormous amounts of mass into surrounding space. Where the two winds collide, conditions become extreme. The impact zone compresses and heats the gas to temperatures of tens of millions of degrees Celsius, hotter than the cores of many ordinary stars. This superheated region emits intense X-rays that travel across 7,500 light-years and reach detectors around Earth. That signal changes predictably throughout the orbital cycle. As the stars move closer together and farther apart, the shape and intensity of the X-ray emission shifts in response. Brightness rises, then it falls. Patterns repeat. For astronomers, the collision zone became something precious, a measurable clock hidden inside chaos. But the companion may be doing more than creating X-rays. Many researchers suspect Eta Carinae b actively influences the instability of the larger star itself. During periastron, its gravitational pull may disturb the already fragile outer layers of Eta Carinae A, amplifying eruptions or reshaping expelled material as it escapes into space. Yet we still cannot observe the companion directly. The primary star overwhelms it visually, and the surrounding dust obscures much of the system. Almost everything known about Eta Carinae b comes indirectly through spectroscopy, orbital calculations, and X-ray analysis. Spectroscopy means studying how matter absorbs and emits light at different wavelengths, allowing astronomers to infer physical properties from distant signals. So we are left reconstructing half the system from shadows and consequences. Two of the most massive stars in the galaxy circle each other continuously, shaping one another through gravity, radiation, and wind. We can clearly see only one of them. The other reveals itself indirectly through disturbances left behind in the surrounding storm. For nearly half a century after the Great Eruption, Eta Carinae seemed quieter, dimmer, exhausted, perhaps. Then, in 1890, the system erupted again. The second event never reached the terrifying brilliance recorded in the 1840s, but observers still watched the star brighten noticeably against the southern sky. Energy surged outward once more. Additional material escaped the system. Another wound opened around the star. What initially appeared to be a lesser aftershock gradually became something more important. Evidence of repetition. Modern telescopes reveal structures extending beyond the main homunculus nebula, tangled clouds, and fast-moving filaments called the outer ejecta. These shells contain material expelled during later eruptions, including the event of 1890. They travel outward at varying speeds, suggesting multiple episodes of mass loss unfolding across different centuries. Astronomers needed a way to separate these layers chronologically. They turned to Doppler shift, the same physical principle that lowers the pitch of a passing ambulance siren as it moves away from you. Applied to light instead of sound, Doppler measurements reveal whether material is moving toward or away from Earth and how quickly. By measuring those velocity shifts carefully across different regions, researchers reconstructed the timing of individual ejection events surrounding Eta Carinae. The results were deeply unsettling. Some of the outer material proved significantly older than the 19th century eruptions. Certain shells appeared to originate from the 1300s and 1600s, centuries before European observatories regularly monitored southern skies. Eta Carinae had already been erupting violently long before anyone recorded it. The Great Eruption was not an isolated catastrophe. It was one chapter in a much longer history. That realization changed the entire interpretation of the system. Instead of a singular stellar accident, astronomers began seeing a recurring pattern of escalating instability. Eta Carinae had likely spent hundreds of years shedding mass episodically, each eruption stripping away more material from the star's outer layers. But the chronology was not the only discovery hidden in the ejecta. The chemistry differed from shell to shell. Using spectroscopy, the study of how matter emits and absorbs light at specific wavelengths, astronomers measured varying abundances of nitrogen, carbon, and oxygen throughout the surrounding clouds. Those chemical differences revealed where inside the star the material originally came from. The oldest ejecta contained matter associated with shallower outer layers. Newer eruptions exposed material forged deeper inside the star itself. Each event appeared to excavate progressively lower regions, peeling away the stellar structure layer by layer across centuries. You can almost imagine the star turning itself inside out. That pattern carries enormous implications for stellar evolution. Massive stars maintain separate internal zones where different fusion processes occur. As deeper layers become exposed, astronomers gain indirect evidence about what the hidden interior is doing long before the final collapse begins. But there is another side to that knowledge. The closer eruptions cut toward the core, the closer Eta Carinae moves toward the region where stable fusion eventually fails. The core is not merely the center of the star. It is the place where gravity waits patiently beneath every temporary balance, compressing matter toward conditions that no eruption can reverse indefinitely. Deep inside the chaos surrounding Eta Carinae, there is one phenomenon astronomers can predict almost to the month. Every 5.54 years, the X-rays fade. The pattern repeats with astonishing regularity. As the two stars approach periastron, their closest orbital passage, the powerful X-ray emission generated between them suddenly collapses. For roughly 3 months, the signal drops close to zero before gradually recovering again. Researchers call this interval the X-ray minimum. It became one of the most important discoveries in the study of the system because, for the first time, Eta Carinae revealed a measurable rhythm hidden beneath the instability. The eruptions remained unpredictable. The brightness changes remained complicated, but the orbital cycle created a repeating clock astronomers could organize around. Observation campaigns suddenly became coordinated instead of reactive. The explanation begins in the collision zone between the two stellar winds. Eta Carinae A produces an enormous outflow of relatively slow, dense material. The companion star generates a faster but thinner wind moving through surrounding space at much higher speeds. Where those winds crash together, temperatures rise into the tens of millions of degrees, hot enough to emit intense X-rays detectable across the galaxy. But as the stars draw extremely close during periastron, the balance shifts. The heavier wind from the primary overwhelms the companion's faster stream. The collision region destabilizes and collapses entirely, extinguishing the superheated X-ray source, almost like a flame deprived of oxygen. For a brief interval, the system's most energetic signal simply disappears. Then it returns. The Chandra X-ray Observatory has now monitored multiple complete cycles of these minimum events across decades of observation. Chandra was launched by NASA in 1999, specifically to study high-energy regions of the universe, invisible to ordinary optical telescopes. Eta Carinae quickly became one of its most important long-term targets. What emerged from the data was subtle, but deeply important. No two X-ray minimums are perfectly identical. Some begin slightly earlier, others recover more slowly. Tiny variations appear in brightness, timing, and the shape of the returning signal after periastron passes. These differences imply that one or both stellar winds are gradually changing over time. And changing winds imply changing stars. That possibility transformed the meaning of the orbital clock. Astronomers were no longer just tracking repetition. They were measuring evolution in progress, watching a system drift slowly toward conditions not yet fully understood. The 2020 Periastron campaign became the most comprehensive observation effort ever attempted for Eta Carinae. Chandra monitored the X-ray collapse, while Hubble observed ultraviolet changes and ground-based telescopes collected spectroscopic data simultaneously across multiple continents. Even now, years later, researchers continue analyzing material gathered during that single orbital passage. Papers are still emerging. The X-ray minimum has become more than a predictable astronomical event. It functions almost like a pulse, repeating every 5.5 years through the expanding dust and turbulence. Each cycle gives astronomers another opportunity to compare the system against its earlier state, searching for tiny deviations that might reveal how a star, this unstable, changes as it moves deeper into the final phases of its life. Brightness sounds simple from Earth. A star either shines strongly or it does not. But with Eta Carinae, even light behaves like evidence from an unresolved case. Since roughly 1998, astronomers have watched the system grow steadily brighter, not rhythmically, not according to the familiar orbital cycle already mapped through X-rays. This change unfolds over decades, slowly enough to notice only through continuous observation, yet consistently enough that the trend can no longer be dismissed as noise. The star is waking up again. For most of the 20th century, Eta Carinae remained invisible to the naked eye despite its enormous intrinsic luminosity. Dust from earlier eruptions obscured much of the visible light escaping the system. But under dark southern skies today, the star has become visible once more. Something is changing inside the nebula. Hubble observations between 1998 and 2012 revealed that the ultraviolet brightness of the central source approximately doubled during that interval. Ultraviolet light, more energetic than visible light, allowed astronomers to isolate the interstellar region from surrounding ejecta with far greater precision. The increase was measurable, repeated, persistent. Naturally, researchers proposed competing explanations. One possibility is comparatively simple. The expanding dust shells from earlier eruptions may be thinning gradually as they move outward through space, allowing more existing starlight to escape toward Earth. In that scenario, Eta Carinae itself is not fundamentally changing. We are simply seeing more clearly through the debris surrounding it. But another interpretation carries far heavier implications. The star itself may actually be increasing in luminosity. To test this, astronomers designed Hubble observing campaigns specifically intended to separate genuine stellar brightening from dust clearing effects. By analyzing particular spectral signatures, meaning distinct wavelength fingerprints emitted by the star rather than the surrounding nebula, researchers found evidence suggesting the central source truly is becoming more luminous, independent of the expanding dust. That result unsettled many in the field, because if Eta Carinae is intrinsically brightening, the process implies rising instability deep within the system itself. Massive stars already exist in precarious balance between radiation and gravity. Increasing luminosity means increasing outward pressure, increasing turbulence, and potentially increasing rates of mass loss. No other known star at this evolutionary stage has displayed brightening quite like this, and the trend has not stopped. Each monitoring cycle records the system slightly brighter than before, not dramatically brighter overnight, but incrementally enough that long-term comparison becomes impossible to ignore. The change accumulates year after year, like pressure building invisibly beneath a surface. That gradual consistency altered the psychology surrounding Eta Carinae research. Earlier generations approached the system as a fascinating object requiring patient observation across astronomical timescales. But the brightening introduced a different feeling entirely. Researchers were no longer only preserving data for distant future astronomers. They were watching a measurable evolution occurring within a human lifetime. And no one can yet say exactly what the increase means. Perhaps the system is reorganizing itself after earlier eruptions. Perhaps the stellar wind structure is changing. Perhaps deeper layers inside the primary star are entering a new, unstable phase entirely. The data continues accumulating, quietly and relentlessly, while the central source grows brighter behind the drifting debris that once concealed it almost completely. At the center of Eta Carinae, far beneath the turbulence, the star is running through a sequence that every massive star eventually follows. The details differ, the timing changes, but the direction never reverses. Fusion always moves forward. A star lives by nuclear fusion, the process where lighter atomic nuclei combine into heavier ones under extreme temperature and pressure. That reaction releases energy, and the outward energy flow temporarily balances gravity. As long as fusion continues, the star survives. Our sun still fuses hydrogen into helium quietly and efficiently. It has enough hydrogen remaining for another 5 billion years of stable existence, but stars as massive as Eta Carinae consume fuel with astonishing speed. Greater mass means stronger gravity, higher core temperatures, and dramatically accelerated fusion. The star burns through entire stages of existence almost recklessly. Hydrogen disappears first. Once the hydrogen in the core becomes depleted, gravity gains ground. The core contracts inward, pressure rises, temperatures climb further, and helium fusion ignites. Helium nuclei combine into carbon and oxygen during a phase lasting hundreds of thousands of years. Then the sequence accelerates. Carbon fusion begins next, producing elements like neon and magnesium. That stage may last only thousands of years. After carbon comes neon burning, then oxygen, then silicon. Each new phase unfolds faster than the last because every heavier fuel releases less energy while demanding even greater temperatures to ignite. The star enters a kind of desperate compression cycle. Gravity squeezes inward, temperatures spike. Another fuel ignites briefly, Then the process repeats with increasing urgency. By the silicon burning stage, the timetable has become almost absurdly short. Silicon fusion lasts roughly 1 day inside a massive star before the core chemistry reaches its final destination. Iron. Iron changes everything because fusing iron does not release energy. It consumes it. For the first time in the star's life, nuclear reaction stops supporting the crushing weight above the core. Fusion ceases to function as a defense against gravity. And gravity does not pause. The iron core continues growing until it approaches approximately 1.4 solar masses, a threshold known as the Chandrasekhar limit. Beyond that point, electron pressure, the quantum mechanical resistance supporting the core against collapse, can no longer withstand the inward force. The entire core fails in less than 1 second. Matter accelerates inward at roughly a quarter of the speed of light. Temperatures surge into billions of degrees. Atomic nuclei are crushed together so violently that electrons and protons merge into neutrons. The core collapses into an object only a few kilometers across, while containing more mass than the Sunday. Everything above it is still falling. Then the collapse stops abruptly against the incompressible neutron core, generating a shock wave that tears outward through the star's interior. Neutrinos flood into space. Energy erupts outward. Outer layers are blasted apart across interstellar distances. Every visible feature of a supernova begins there, inside that single, irreversible moment when the core loses its ability to resist gravity. Eta Carinae has not reached that point yet. Fusion still continues somewhere beneath the instability and mass loss, but the sequence is already underway deep inside the star. Massive stars do not escape this progression. They only move through it at different speeds, carrying their enormous cores toward the same final surrender to physics. Astronomy usually builds categories slowly. A few unusual objects appear, patterns emerge across decades, and eventually a formal classification takes shape. But the category called supernova imposter began almost backward. First came Eta Carinae. Then came the attempt to explain it. The eruption recorded during the 19th century resembled a supernova in brightness and violence. Historical observations showed enormous energy release, dramatic brightening, and catastrophic mass ejection. By every outward appearance, the star seemed to be dying, except it survived. That survival created a problem. A true supernova destroys the original star completely. The core collapses, the outer structure is unbound, and only a neutron star or black hole remains. But Eta Carinae endured after the eruption ended. The system remained active, unstable, and very much alive. Astronomers eventually needed a separate term for events that imitate stellar death without completing it. So the phrase supernova imposter entered astrophysics. The name sounds almost playful, but the underlying physics is deeply uncomfortable. A supernova imposter releases energy approaching supernova scales and ejects huge amounts of material into surrounding space, yet somehow avoids full structural destruction. According to simplified stellar models, that should be extremely difficult to achieve. The mechanism remains uncertain even today. Several competing explanations attempt to describe how such eruptions occur. One possibility involves explosive nuclear burning igniting in outer stellar layers rather than deep inside the core. Another focuses on internal gravity waves, oscillations generated near the core that carry enormous energy outward through the star until surface layers are blown away. Then there is the Super Eddington wind model. In that scenario, Luminosity rises so dramatically that radiation pressure drives matter outward in a sustained eruption rather than a single terminal explosion. The star effectively overwhelms its own atmosphere and begins shedding mass continuously at extraordinary rates. Each model predicts different ejecta structures, different chemical signatures, and different velocity profiles in the expelled material. That is why the homunculus nebula matters so much scientifically. Researchers compare theoretical predictions against the actual geometry and composition of the surrounding gas, searching for evidence favoring one mechanism over another. But Eta Carinae complicated the story further by erupting repeatedly. The events of 1843 and 1890 were not isolated accidents, and older ejecta demonstrate the system had been unstable centuries earlier. Whatever process drives these eruptions appears capable of recurring multiple times within the same star. That realization shifted supernova imposters away from the idea of rare structural failure towards something cyclical and dynamic. Eventually, astronomers began discovering similar objects in other galaxies. Events designated SN 2006 JC and SN 2009 IP displayed related behavior, bright precursor eruptions, followed by unusual mass loss and extreme luminosity changes. These detections confirmed that Eta Carinae was not entirely unique. Supernova imposters represented a genuine class of stellar phenomenon occurring across the universe. Yet Eta Carinae still dominates the field. It remains the closest known example, the brightest, and by far the most thoroughly observed. Every newly discovered imposter event is measured against the benchmark established by this one system hidden inside the Carina Nebula. And despite more than a century of analysis, the archetype itself still refuses to settle cleanly into theory. In 2006, light from a distant galaxy reached Earth, carrying evidence of a stellar catastrophe so extreme that astronomers initially struggled to believe the measurements were correct. The event was designated SN 2006 Jai. It occurred in the galaxy NGC 1260, approximately 238 million light-years away. Even across that immense distance, the explosion became one of the brightest supernovae ever recorded at the time. Peak luminosity exceeded that of ordinary core collapse supernovae by roughly 100 times. The energy release was staggering. For weeks, theoretical papers appeared almost faster than observations could be analyzed. Existing models strained to explain how a single star could generate so much light without violating known physical constraints. But the deeper shock arrived when astronomers examined archival data of the progenitor star that existed before the explosion. It appeared to be a luminous blue variable, the same classification as Eta Carinae A. That similarity immediately drew attention because the precursor behavior surrounding SN 2006 Jai looked strangely familiar. Before the terminal explosion occurred, the star underwent a major brightening phase, resembling a supernova imposter eruption. Massive amounts of material were expelled into surrounding space before the final collapse happened. Then the star exploded for real. That sequence altered the conversation around Eta Carinae almost overnight. Until then, many researchers viewed giant eruptions as phenomena potentially separated from stellar death by enormous spans of time. Thousands or even millions of years might intervene between instability and final collapse. But SN 2006 Jai suggested something far less comfortable. The interval between precursor eruption and terminal explosion may sometimes span only years or decades. If Eta Carinae follows a comparable evolutionary path, then the eruption witnessed during the 19th century may not represent a distant warning at all. It could belong to the final stages of the star's life already unfolding beneath the surface. Astronomers became careful with their language after that realization. Few researchers publicly claimed Eta Carinae was about to explode. The uncertainties remained enormous. Internal stellar conditions cannot be measured directly, and massive stars often behave unpredictably for long periods before collapse. But the possibility could no longer be dismissed casually. The comparison became even more unsettling when researchers estimated what SN 2006G would have looked like at Eta Carinae's distance from Earth. The explosion would have rivaled moonlight in brightness, casting visible shadows at night and remaining brilliant for months across the sky. Human civilization would have watched the event directly. Several prominent studies eventually described SN 2006 Gi as the best available analog for Eta Carinae's eventual death. Not identical, certainly. Every massive star evolves differently depending on rotation, mass loss, magnetic fields, and binary interactions. But structurally, the resemblance between the systems was impossible to ignore. Two unstable luminous blue variables, precursor eruptions, massive ejecta shells, extraordinary luminosities. The pattern aligned too closely. What SN 2006 Gi ultimately proved was not that Eta Carinae will explode tomorrow, next century, or even within human history. The evidence does not support certainty on that scale, but it demonstrated something equally important. A star remarkably similar to Eta Carinae can transition from violent instability to complete destruction on timescales short enough to matter emotionally to the people studying it. Imagine a star so unstable that it spends millions of years trying to throw itself away. That is essentially what Eta Carinae has been doing since it formed. Even in periods without major eruptions, the primary star loses mass continuously through its stellar wind, a powerful stream of charged particles escaping the surface at enormous velocities. The outflow is so extreme that Eta Carinae A sheds roughly the equivalent of our Sun's entire mass every 1,000 years. Not occasionally, constantly. Over astronomical timescales, that rate becomes staggering. Long before the 19th century eruptions, the star had already been stripping itself layer by layer into surrounding space. Then came the catastrophic mass ejections associated with the Great Eruption, the later outburst in 1890, and the older shells discovered farther from the system. Together, they changed the star fundamentally. Astronomers estimate Eta Carinae may have formed with roughly 150 solar masses. Today, it likely contains somewhere between 100 and 120. In other words, the star visible now is already a reduced version of the object originally born inside the Carina Nebula. And that reduction matters enormously. The final fate of a massive star depends heavily on how much mass remains when core collapse eventually begins. The iron core forming deep inside Eta Carinae grows according to the balance between nuclear fusion, gravity, and mass loss. If enough outer material is shed before collapse, the resulting explosion may produce a neutron star rather than a black hole. The entire ending changes. A neutron star is an ultra-dense stellar remnant composed mostly of neutrons packed together after collapse. A black hole forms when gravity overwhelms even that compressed matter, creating a region where escape becomes impossible. Which outcome Eta Carinae reaches may depend partly on how successful the star is at becoming smaller before time runs out. But the mass loss rate itself refuses to stay stable. The stellar wind fluctuates. Eruptions accelerate the process dramatically. Binary interaction during periastron appears capable of disturbing the outer atmosphere and altering outflow patterns. Instead of a smooth decline, Eta Carinae loses mass through chaotic pulses and shifting intensities. That variability makes precise measurements difficult. The homunculus nebula complicates things further by obscuring the inner wind region where much of the activity occurs. Visible light cannot penetrate the surrounding dust cleanly, forcing astronomers to rely on radio and infrared observations. Infrared wavelengths are longer than visible light and can pass more effectively through dusty environments, allowing researchers to probe hidden structures closer to the central stars. Even then, uncertainties remain large. Researchers can estimate how much matter escapes the system, but exact values continue changing as new data arrives. Every revised measurement slightly alters predictions about the star's eventual collapse, its remaining lifespan, and the kind of remnant it may leave behind. In a sense, Eta Carinae is competing against itself. The core continues evolving toward gravitational collapse, while the outer layers struggle to escape into space quickly enough to alter the final conditions before that moment arrives. One process moves inward, the other outward. And somewhere between those competing directions lies the future object that will eventually occupy the center of the Carina Nebula thousands of years from now. We tend to imagine stellar death as something spectacular, a final explosion, expanding fire, shock waves crossing interstellar space. But some massive stars may end differently. They vanish. Over the last 2 decades, astronomers monitoring nearby galaxies began noticing an unsettling pattern. Certain massive stars appeared healthy, stable, and carefully cataloged for years, only to disappear from later observations without any visible supernova accompanying the event. No explosion was seen, no bright remnant emerged, just absence. The leading explanation is called a failed supernova. In this scenario, the collapsing iron core forms a black hole so rapidly that the outward shockwave never fully escapes the star. Gravity overwhelms the explosion before it can develop properly, swallowing the outer layers inward instead of blasting them into space. The star effectively collapses into itself. Rather than producing a brilliant optical display, the event may generate only a brief infrared glow as material falls inward and heats temporarily during collapse. Infrared light consists of longer wavelengths associated with heat, capable of escaping dusty regions more effectively than visible light. After that short brightening, the star simply fades from view. The clearest candidate so far is an object known as N6946bh, one inside the galaxy NGC 6946. Astronomers observed the star brightening around 2009. It appeared to be entering a late evolutionary phase. But by 2015, the star was gone. No visible supernova had occurred. Follow-up infrared observations detected only faint residual emission, consistent with matter continuing to fall into a newly formed black hole. That discovery changed how researchers think about massive stellar death. It also inspired dedicated search programs. The Large Binocular Telescope Obituary Survey was created specifically to identify disappearing stars by repeatedly imaging nearby galaxies and comparing catalogs over time. The project's purpose sounds almost surreal, a telescope campaign devoted to finding stars that quietly cease to exist. Eta Carinae occupies an uncomfortable position within this discussion. Most models still favor some form of visible explosion because the system remains unstable, luminous, and heavily enriched with expelled material. But its mass sits near the boundary where failed collapse becomes theoretically plausible. The exact outcome depends on factors still poorly constrained, including rotation, internal structure, and how much mass remains when collapse finally begins. So the silent scenario cannot be ruled out, and that possibility carries unusual emotional weight for the astronomers studying the system. Researchers have openly discussed it in papers and interviews. The unsettling idea that the most anticipated stellar death in modern astronomy might produce almost no visible spectacle at all. Imagine centuries of observation ending not with brilliance, but with disappearance. No blazing object dominating the southern sky. No naked eye supernova. No dramatic cosmic finale. Only a subtle infrared pulse, followed by gradual darkness where a famous star once existed. The universe permits that outcome. Physics does not guarantee beauty, narrative closure, or human satisfaction. Gravity only follows its equations to completion. And in Eta Carinae's case, one possible completion leads not toward explosion, but toward silence, so complete that the star withdraws entirely behind the event horizon of its own black hole. There is another possibility for Eta Carinae, one far more violent than quiet collapse. A hypernova. The term describes an explosion vastly more energetic than an ordinary core collapse supernova, powerful enough to briefly rival the light output of an entire galaxy. Hypernovae are rare, but when they occur, they become some of the brightest events the universe can produce. The process begins with rotation. If a massive star collapses while spinning rapidly enough, the infalling material cannot fall directly into the newly forming black hole. Instead, it forms an accretion disk, a rotating structure of superheated gas spiraling around the center. Magnetic fields and angular momentum then channel part of that material into two narrow jets erupting outward along the star's rotational poles. Those jets travel near light speed. As they punch through the collapsing star and burst into surrounding space, they release intense gamma radiation. Gamma rays are the highest energy form of electromagnetic radiation known in nature. A focused beam of them, sustained for several seconds or minutes, becomes what astronomers call a gamma ray burst. These bursts are detectable across billions of light years. For a brief period, they can outshine almost everything else in the observable universe. The energy involved is so extreme that if a long-duration gamma-ray burst were directed toward Earth from only 7,500 light-years away, the consequences for our atmosphere would be severe. Models suggest the ozone layer could be heavily damaged across the hemisphere facing the burst. Increased ultraviolet radiation from the sun would then reach the surface, disrupting ecosystems and potentially triggering widespread biological stress. But direction matters enormously. Gamma ray bursts are not emitted equally in every direction. They behave more like cosmic searchlights than expanding spheres. Most of the energy remains confined within the narrow jets aligned to the collapsing star's rotation axis. And Eta Carinae's axis appears safely misaligned with Earth. Astronomers inferred this orientation from the elongated structure of the homunculus nebula surrounding the system. The nebula's twin lobes trace the probable direction of the rotational poles, and those poles do not point toward our planet. Multiple peer-reviewed studies have concluded that the risk of a direct gamma-ray burst impact from Eta Carinae is extremely low, so Earth is likely safe. But the hypernova scenario itself remains scientifically plausible. Eta Carinae possesses many characteristics associated with known hypernova progenitors. It is enormously massive, unstable, rapidly losing material, and shaped by intense binary interaction. Those conditions resemble systems observed before extreme explosions in distant galaxies. What remains uncertain are the hidden variables. Researchers still cannot directly measure the core's final rotation speed or determine exactly how much mass will remain at collapse. Those unseen parameters may ultimately decide whether Eta Carinae becomes a standard supernova, a failed collapse, or a hypernova launching relativistic jets into the surrounding galaxy. And so, the range of possibilities remains astonishingly wide. At one extreme lies near silence, a star fading invisibly into a black hole. At the other lies the most energetic stellar explosion our cosmic neighborhood could plausibly experience. Between those outcomes stands a system still evolving behind layers of dust, carrying answers physics has not yet allowed us to see. On the 23rd of February, 1987, a point of light appeared in the southern sky where no bright star had been visible before. The explosion came from the Large Magellanic Cloud, a small satellite galaxy orbiting the Milky Way, roughly 168,000 light-years from Earth. The event was designated Southern 1987A, and within hours it became visible to the naked eye across the southern hemisphere. For many people, it was beautiful. For astronomers, it was transformative. No supernova that close had been observed since the invention of the telescope. For the first time in human history, modern scientific instruments were already operating when a nearby massive star died. Telescopes, spectrographs, particle detectors, and radio observatories suddenly found themselves recording a stellar collapse in real time. But the most important signal arrived before anyone saw light. 3 hours earlier, neutrino detectors buried underground in Japan and the United States registered a tiny burst of particles. Only about 24 neutrinos were detected altogether, astonishingly few considering the scale of the explosion itself. Yet those particles changed astrophysics permanently. Neutrinos are nearly massless subatomic particles produced in enormous quantities during core collapse. Unlike photons, which struggle through the dense outer layers of a dying star, neutrinos pass outward almost immediately because they interact extremely weakly with matter. They escape first. That tiny burst confirmed decades of theoretical work describing how massive stars collapse internally before exploding outward. It also established a practical principle with enormous implications for future observations. A neutrino signal can warn us that a supernova has begun before visible light emerges from the star. SN 1987. A produced another surprise as well. Archival photographs identified the progenitor star as Sandalik 69202, a blue supergiant rather than the red supergiant many models had predicted. That discovery forced theorists to broaden their assumptions about which stars could produce core collapse supernovae. Eta Carinae suddenly seemed more relevant. As a luminous blue variable, Eta Carinae shares several structural characteristics with Sandolik 69202, including extreme mass and unusual atmospheric instability. While the systems are not identical, SN 1987A became the closest observational analog available for understanding what Eta Carinae's death might resemble. The remnant still expands today. Concentric rings of gas surrounding the explosion site continue glowing as the outward shock wave slams into material expelled before the star died. Those rings have been monitored for decades, providing a slow-motion record of how stellar explosions interact with their own earlier mass loss. The resemblance to Eta Carinae's surrounding ejecta is difficult to ignore. Researchers studying the Carina system realized something profound after 1987. The warning signs of stellar death are observable if instruments are already watching carefully enough. Neutrinos arrive early. Shock waves interact with older material predictably. Massive unstable stars leave detectable evidence before collapse occurs. SN 1987. A demonstrated that the universe provides advance notice. And because of that single event, astronomers began constructing a global system designed to ensure that when Eta Carinae eventually reaches its final moment, humanity will not miss the beginning. Deep beneath mountains, inside abandoned mines, and shielded underground chambers, enormous instruments sit in permanent darkness, waiting for a signal that may arrive tomorrow or thousands of years from now. They are listening for neutrinos. The brief warning provided by SN 1987 changed astronomy permanently because it proved that collapsing stars announce themselves before visible light escapes. That discovery eventually led to the construction of a coordinated global monitoring system designed specifically to catch the next nearby stellar death at its earliest moment. The system is called SNOOZE, the Supernova Early Warning System. Operational since 2005. SNOOZE links neutrino detectors across multiple continents into a single automated network. When several facilities detect matching neutrino bursts simultaneously, the system immediately distributes alerts to observatories around the world. The upgraded version, SNOOZE 2.0, launched in 2021. It improved sensitivity, reduced false alarms, and shortened response times dramatically. Today, the interval between confirmed detection and worldwide notification is measured in seconds rather than minutes. For astronomers monitoring Eta Carinae, those seconds matter. The detectors themselves are extraordinary structures. Super Kamiokande in Japan contains 50,000 tons of ultra-pure water sealed inside a gigantic underground chamber beneath Mount Ikano. Thousands of light sensors line the walls, waiting for the faint flashes produced when neutrinos interact with water molecules. Because neutrinos pass through ordinary matter almost effortlessly, the detector must be immense to capture even a tiny fraction of them. Other facilities contribute continuously. Borizzino in Italy monitors liquid scintillator, a material that emits tiny bursts of light during particle interactions. NOVA in the United States stretches across northern Minnesota with long detector arrays designed partly for neutrino research. SNO Plus in Canada operates deep underground inside a former nickel mine, shielded from cosmic interference by kilometers of rock. Most of the time, the detectors record almost nothing unusual. But if multiple observatories register coincident neutrino bursts simultaneously, the statistics become overwhelming. Random background noise cannot reproduce the same signal pattern across separated continents. A genuine stellar collapse becomes immediately recognizable, and the alert would arrive before the sky changed. Hours before Eta Carinae brightened visibly, telescopes could already be repositioning toward the Carina Nebula. Spectrographs would activate, space telescopes would reorient. Observatories across Earth would prepare to capture the first optical moments of a supernova in human history using fully modern instrumentation. That possibility is why the network never sleeps. These detectors operate continuously, every hour of every day, despite immense maintenance costs and technical complexity. Super Kamiokande itself underwent upgrades, partly motivated by the expectation that the next Milky Way supernova could come from Eta Carinae. The system remains the primary nearby candidate, so the infrastructure already exists. Buried under mountains and shielded beneath stone, humanity has built an early warning system for the death of a star 7,500 light years away. The instruments are running now, tonight, listening for particles that travel ahead of light itself. Only one variable remains unknown. Somewhere inside Eta Carinae, beyond direct observation, physics continues unfolding toward an answer the detectors were built to hear first. For most of human history, nebulae were only images, glowing shapes, suspended against black space with no visible depth. Eta Carinae's surrounding cloud looked similar at first, a strange bipolar structure hanging in the Carina Nebula. But modern instruments changed the perspective entirely. Astronomers no longer study the homunculus as a flat object. They now map it in 3 dimensions, measuring not only where the gas appears in the sky, but how fast every region is moving toward or away from Earth. The technique depends on spectroscopy. A spectrograph separates light into its component wavelengths, allowing researchers to measure tiny shifts caused by motion. Gas moving toward us compresses its wavelength slightly. Gas moving away stretches them. By combining thousands of these measurements across the nebula, astronomers reconstructed the eruption's full spatial geometry. The European Southern Observatory's VLT-X shooter instrument became especially important for this work. Mounted on the Very Large Telescope in Chile, it tracked molecular hydrogen throughout the homunculus at extremely fine velocity resolution, producing something close to a topographic map of the explosion itself. And the structure turned out to be messy. The twin lobes are not smooth balloons, expanding evenly into space. They contain trenches, ridges, dents, protrusions, and irregular scars frozen into the gas. Turbulence from the eruption remains preserved within the expanding material, like fingerprints left behind by the violence that created it. Then researchers discovered another layer entirely. Outside the main lobes sits a thinner outer shell racing outward at roughly 3,200 kilometers per second, far faster than most of the homunculus itself. The velocity suggests a separate ejection event occurring after the primary eruption, superimposed onto the earlier structure like a second blast wave overtaking the first. Hubble observations added another surprise. Ultraviolet imaging revealed warm magnesium gas, occupying regions where no emission had been expected. The material fills gaps between the central lobes and surrounding nitrogen filaments heated by shocks. Those unexpected structures appear to trace collision zones where different layers of ejecta slammed into one another at varying speeds. The nebula's waste tells its own story. A dense equatorial disk circles the middle region between the two lobes, containing far more material than surrounding areas. The asymmetry strongly supports the idea that the companion star influenced the eruption gravitationally, redirecting expelled matter preferentially along the orbital plane rather than evenly across all directions. Because the velocities are now mapped directly, astronomers can calculate the eruption's kinetic energy instead of estimating it only from brightness. Kinetic energy measures energy carried by motion itself. When researchers added together the observed speeds and masses of the ejecta, the result approached 10 to the 50th ergs, comparable to the energy of a genuine supernova. Yet the star survived. The 3-dimensional maps continue revealing additional puzzles as well. At the outer edge of the nebula, astronomers identified diffuse material moving at intermediate velocities that fits neither the primary homunculus nor the fast outer shell cleanly. Those structures remain under active investigation. Even after decades of study, the nebula still contains features nobody predicted. And that may be the most revealing detail of all. When the James Webb Space Telescope began science operations in 2022, astronomers immediately pointed it toward regions filled with dust. That was where Webb could do what earlier telescopes could not. Unlike Hubble, which primarily observes visible and ultraviolet light, Webb specializes in infrared wavelengths. Infrared light has longer wavelengths that pass through dust clouds far more effectively, allowing the telescope to peer into regions previously hidden behind opaque curtains of gas and debris. The Carina Nebula became one of Webb's first major targets. Images released in July 2022 revealed thousands of young stars embedded deep inside dusty molecular clouds. Entire stellar nurseries appeared, where earlier instruments had seen only darkness. Structures inside the nebula gained depth, texture, and thermal detail impossible to capture with visible light alone. For Eta Carinae, the implications were enormous. The homunculus nebula surrounding the system contains dense dust layers that block direct optical observation of many inner regions. Webb's infrared sensitivity changes that completely. Instead of viewing only reflected light from outer surfaces, astronomers can now trace thermal emission from warm dust distributed throughout the expanding ejecta. Thermal emission is heat radiation. Dust grains, warmed by nearby stars, emit infrared light depending on their temperature. By mapping those emissions precisely, Webb allows researchers to measure how energy moves through different regions of the nebula and how the expelled material is structured internally. Some of the most important observations focus on the inner wind zone. This region surrounds the binary stars themselves, where the two stellar winds collide violently before cooling and condensing into dust farther outward. It forms a transition boundary between the extremely hot X-ray producing gas and cooler matter capable of forming molecules and grains. Webb can probe that boundary directly. The telescope also resolves faint structures within the outer ejecta with remarkable clarity. Those older shells, expelled centuries before the Great Eruption, may now be dated more accurately by analyzing temperature distributions, expansion geometry, and chemical composition in greater detail than previously possible. And there is another advantage. Hubble has been monitoring Eta Carinae since the early 1990s. That long observational archive now combines with Webb's new infrared data to create direct before and after comparisons spanning more than 30 years. Researchers can measure how different regions of the homunculus have expanded, shifted, cooled, and interacted over time. The system is no longer static. It becomes measurable change across decades. Attention is already turning toward the next periastron passage, expected around 2032. That event will be the first observed with Webb operating at full scientific capability, alongside upgraded X-ray facilities and new generations of ground-based observatories. Planning documents for coordinated campaigns are already circulating within the research community. What excites astronomers most is not simply improved image quality. Webb represents an entirely different category of information. Previous periastron observations lacked access to these infrared diagnostics completely. Entire physical regions of the system were effectively invisible before now. So, for all the decades spent studying Eta Carinae, parts of the story may still remain hidden behind dust. And for the first time, humanity possesses an instrument capable of looking through it. Calendars inside major observatories already contain entries for an event still years away. 2032. That is when Eta Carinae's binary orbit will carry the two stars back into periastron, their closest approach during the 5.5 4-year cycle. Periastron passages have been monitored carefully for decades because they produce dramatic changes in X rays, stellar winds, and emission lines throughout the system. But the coming passage feels different. Astronomers rarely speak emotionally about scheduled observations. Most telescope campaigns are simply opportunities to gather data. Yet, discussions surrounding the 2032 event often carry a different tone, something closer to anticipation than routine planning. Part of that comes from the instruments now becoming available. For the first time, Eta Carinae will be observed during periastron using the James Webb Space Telescope at full operational capability. New generations of extremely large ground-based telescopes are also approaching completion. These facilities use segmented mirrors spanning dozens of meters, collecting vastly more light than previous observatories. The detector network has evolved too. Neutrino observatories are more sensitive than they were during earlier orbital cycles. X-ray instruments have improved temporal resolution and spectral precision. Radio interferometers can now map structures with astonishing detail across multiple wavelengths simultaneously. Observation proposals are already circulating through the research community. Large telescope facilities allocate observation time years in advance because demand is immense. Researchers studying Eta Carinae are already coordinating multi-observatory campaigns for the expected periastron window, aligning schedules across continents and space-based platforms long before the stars actually approach each other. The primary question centers on change. Has the wind structure evolved measurably since the previous close passage in 2020? Even subtle deviations matter. A stellar wind carries information about conditions deep inside the star itself, and changing winds imply changing internal physics. Astronomers will watch the X-ray minimum especially closely. During periastron, the collision zone between the two stellar winds partially collapses, causing the X-ray output to plunge temporarily. If the timing, depth, or recovery profile differs from previous cycles, it would suggest the system is not merely repeating behavior mechanically, it would indicate evolution in progress. Ground-based optical interferometers may provide another breakthrough. Interferometry combines light collected by multiple telescopes to simulate the resolving power of one enormous instrument, spanning the separation distance between them. With sufficient precision, researchers may finally resolve the wind collision region directly rather than inferring its structure indirectly through spectral analysis. That possibility would have sounded impossible only decades ago. Meanwhile, Eta Carinae itself continues brightening gradually across successive observation cycles. If the trend remains consistent through 2032, the system will appear significantly more luminous than during any previously monitored periastron passage. No one expects 2032 to reveal the exact moment of stellar death. The physics does not allow that kind of precision yet, but many researchers suspect the upcoming observations may answer something equally important: whether Eta Carinae is evolving slowly across astronomical timescales or rapidly enough for measurable transformation to occur within a single human lifetime. That distinction changes how we understand the star entirely. Around Eta Carinae, the darkness is crowded with unfinished stars. The Carina Nebula stretches across roughly 300 light-years of space and contains one of the most active star-forming environments in the Milky Way. Massive molecular clouds drift through the region beside young open clusters and luminous blue stars whose radiation reshapes the nebula continuously. Nothing here remains still for long. Eta Carinae dominates much of this environment through energy alone. Its ultraviolet radiation floods surrounding gas clouds with enough intensity to ionize atoms and heat nearby material to enormous temperatures. This process is called photoevaporation, meaning energetic radiation gradually strips matter away from dense clouds and disperses it outward into surrounding space. Over thousands of years, entire structures change shape. Pillars emerge where denser gas resists erosion slightly longer than the material around it. Cavities open through formerly opaque clouds. Bright glowing rims form where hot, ionized gas collides against colder, denser regions. The nebula appears sculpted because radiation from massive stars is actively sculpting it in real time. But destruction is only part of the story. Embedded inside the nebula sits Trumpler 14, a young star cluster containing stars only a few 100,000 years old. In stellar terms, they are newborns. These stars formed inside the same violent radiation field, dominated by Eta Carinae, surviving within an environment that simultaneously tears clouds apart and compresses neighboring regions strongly enough for gravity to trigger collapse elsewhere. One disturbance creates another beginning. The James Webb Space Telescope revealed this process with extraordinary clarity after operations began in 2022. Infrared observations penetrated dust clouds that visible light could not cross, exposing thousands of previously hidden newborn stars scattered throughout the Carina Nebula. Many remained, wrapped inside dense cocoons of gas from which they are still emerging. We are watching stellar birth unfold beside a star, approaching collapse. Eventually, Eta Carinae itself will transform the region again. When the star dies, the resulting shockwave will expand outward through the nebula at thousands of kilometers per second, compressing surviving molecular clouds as it moves. Astronomers expect this pressure wave to trigger additional star formation across parts of the Carina complex. The explosion will also seed the nebula with heavy elements forged deep inside the star's core. Carbon, oxygen, silicon, iron. Those elements will mix into surrounding gas clouds and eventually become part of future planets and stars. This recycling process is how galaxies gradually build chemical complexity over billions of years. Massive stars form, burn rapidly, enrich the interstellar medium, and disappear. Later generations inherit the material left behind. Earth formed through exactly this sequence. Every atom in your body passed through earlier stars before the sun existed. Long before oceans formed here, another massive star lived briefly, died violently, and scattered the raw material that eventually became us. Eta Carinae is simply another link in that chain, feeding future worlds through its own destruction somewhere inside the living structure of the Carina Nebula. Inside modern astronomy, very few objects sustain continuous attention for generations. Most discoveries arrive, produce papers for several years, then slowly fade into background reference material as the field moves elsewhere. Eta Carinae never allowed that to happen. The research community surrounding the star remains surprisingly small. At any given time, perhaps only a few dozen scientists worldwide are deeply focused on the system itself. Most know each other personally. Many have collaborated across decades, sharing telescope campaigns, theoretical models, conference discussions, and orbital predictions that stretch across entire careers. Certain names appear repeatedly through the history of the field. Chris Davidson and Roberta Humphreys at the University of Minnesota became central architects of modern Eta Carinae science during the late 20th century. Their work established much of the theoretical framework that later researchers still operate within today. They helped transform Eta Carinae from an astronomical curiosity into one of the most important laboratories for studying unstable, massive stars. At NASA Goddard Space Flight Center, Theodore Gull led extensive Hubble spectroscopic campaigns that unfolded across years of observation time. Spectroscopy, the technique of splitting light into its component wavelengths, allowed researchers to map ejectochemistry, stellar winds, and velocity structures in extraordinary detail. But those maps required hundreds of individual observations collected patiently across orbital cycles that lasted more than 5 years each. The work demanded unusual patience. Graduate students entered doctoral programs, knowing their subject might suddenly transform while they were still writing dissertations. Some began studying Eta Carinae, fully aware that the star could potentially produce career-defining data before graduation. Others accepted the opposite possibility, that nothing dramatic would happen at all during their lifetimes. But the monitoring never stopped. Funding agencies gradually began treating Eta Carinae observation campaigns less like ordinary research proposals and more like scientific infrastructure. Telescope time continued being renewed decade after decade with remarkably little controversy, despite how competitive major observatories normally become. The reasoning was simple. If the defining event finally arrived while nobody was watching, the loss would be permanent. Senior astronomers who entered the field during the 1980s and 1990s often gave younger researchers the same quiet advice. Structure your career around this star carefully. It may do something extraordinary while you are alive. Now, many of those younger scientists have become senior researchers themselves. They are passing the same warning forward. There is something unusual about a scientific community openly acknowledging that its defining observation could occur tomorrow, or perhaps not for another million years, while continuing the work regardless. Careers, funding cycles, telescope schedules, theoretical models, and international collaborations have all accumulated around a single stellar system located 7,500 light-years away. The vigil continues because uncertainty does not reduce the importance of watching. In some ways, it increases it. Astronomers can recover from missing many discoveries, but Eta Carinae offers only one first moment, and once that moment passes, no instrument in history will ever observe it again. Before anyone sees anything in the sky, detectors beneath mountains and underground laboratories will notice the event first. A sudden burst of neutrinos will arrive at Earth, particles so weakly interacting that they pass through entire planets almost untouched. For several seconds, instruments designed decades earlier for this exact purpose will begin recording the collapse of Eta Carinae's core before light itself escapes the star. Then the waiting will begin. Hours later, the optical brightening will emerge from the Carina Nebula as the expanding shockwave forces the outer layers outward at enormous speed. Gas compressed by the explosion will heat to extraordinary temperatures, producing light visible across 7,500 light-years of space. A star that has remained unstable and partially obscured for centuries will suddenly dominate the night sky. At peak brightness, a standard core collapse supernova from Eta Carinae would outshine every other star visible from Earth. Some models suggest it could rival the brightness of the full moon for days or weeks. Shadows would appear beneath starlight alone. The southern hemisphere would receive the clearest view but the event would remain visible worldwide. People would notice immediately. Cities filled with artificial light would still see it. News broadcasts would interrupt normal programming. Amateur astronomers would carry telescopes outside within minutes. Observatories across Earth and in orbit would pivot toward the same location almost simultaneously, gathering data continuously across every wavelength modern instruments can measure. But the brightness would not vanish quickly. The explosion would likely remain visible to the naked eye for months as the expanding debris cloud continued radiating heat into surrounding space. If the event resembled SN 2006G, the extraordinarily luminous explosion observed in another galaxy, the brightness could persist far longer. That supernova released roughly 100 times more energy than a conventional stellar collapse. An equivalent event at Eta Carinae's distance could remain among the brightest objects in the sky for more than a year. Despite the spectacle, Earth would remain physically safe. The distance is too great for the expanding debris to threaten the solar system, and the probable gamma ray burst axis does not align with our planet. The material ejected during the explosion would require thousands of years to cross even a fraction of the distance separating Earth from the Carina Nebula. Eventually, the brightness would fade. Future generations looking toward that region of sky would no longer see Eta Carinae itself. In its place would remain an expanding remnant nebula, glowing faintly as shock waves continued spreading through surrounding gas. The original star would be gone permanently, and at the center of that expanding debris, hidden from direct view, a black hole would likely remain behind. A compressed remnant formed from a star that spent millions of years resisting its own gravity before finally losing the struggle in a single, irreversible moment visible across the galaxy. Long before planets form, before oceans collect or atmospheres stabilize, massive stars spend millions of years manufacturing the raw materials those worlds will eventually require. Eta Carinae is doing that work now, deep beneath layers of turbulence and radiation that no telescope can see directly. Every eruption from the system carries evidence outward. The homunculus nebula, the expanding outer ejecta, and the constant stellar wind all contain atoms forged inside the star itself. Those atoms were assembled through nucleosynthesis, the process by which stars fuse lighter nuclei into heavier elements under immense pressure and temperature. Massive stars dominate this process throughout galaxies because their cores reach conditions ordinary stars never achieve. Hydrogen becomes helium. Helium becomes carbon and oxygen. Later stages produce neon, magnesium, silicon, sulfur, and eventually iron. Each fusion stage reshapes the chemistry of the star while simultaneously shortening the time remaining before collapse. The universe did not begin with these materials. After the Big Bang, almost all ordinary matter consisted only of hydrogen and helium with traces of lithium. Carbon was absent. Oxygen did not exist. Iron, calcium, phosphorus, and silicon had not yet formed anywhere in the cosmos. Every heavier element required generations of stars to manufacture them gradually across billions of years. You carry those products constantly. The calcium inside human bones, the oxygen moving through blood, and the iron inside every red blood cell were all forged inside ancient stars that died before the sun formed. Their explosions scattered enriched material into space where later stellar systems condensed from chemically altered clouds. Eta Carinae is adding to that inheritance already. Material expelled during the eruptions of the 13th century, the 19th century, and the ongoing stellar wind has seeded the surrounding nebula with newly forged atoms. But the most extreme chemistry still lies ahead. When core collapse finally begins, the explosion itself will trigger additional nucleosynthesis under conditions impossible to sustain during ordinary stellar fusion. Astronomers call part of this process the R process, short for rapid neutron capture. During the explosion, atomic nuclei are bombarded with enormous numbers of neutrons in fractions of a second. Under those violent conditions, elements heavier than iron can form briefly before radioactive decay stabilizes them into recognizable matter. Gold emerges this way. So do platinum and uranium. A wedding ring carries evidence of catastrophe. The gold shaped into jewelry on Earth was forged during a stellar explosion billions of years ago, then scattered across interstellar space before eventually becoming part of the cloud that formed our solar system. Eta Carinae will contribute similar material to future generations of stars and planets, long after humanity disappears. Over millions of years, the debris from its death will mix into new molecular clouds across the Carina region. Some of that matter will collapse into future solar systems, forming rocks, atmospheres, oceans, and perhaps living organisms capable of wondering where their atoms came from. The universe recycles everything slowly, but it wastes nothing. Long before the final explosion arrives, Eta Carinae has already altered astronomy permanently through the questions it forced scientists to confront. The star has spent nearly 2 centuries refusing to behave according to simple models, and in doing so, it has expanded the boundaries of stellar physics itself. The Great Eruption of 1843 changed the field first. Before that event, astronomers had no framework for a star surviving such catastrophic mass loss. The eruption demonstrated that a massive star could brighten dramatically, eject enormous quantities of material, and remain intact afterward. What once appeared unique has since become an entire category of stellar behavior observed across other galaxies. The term supernova imposter exists because Eta Carinae existed first. Later observations deepened the disruption. When the Hubble Space Telescope began studying the Homunculus Nebula in ultraviolet detail during the 1990s, astronomers discovered that the eruption had not expanded symmetrically. The ejecta formed lobes, trenches, and dense equatorial structures instead of a smooth sphere. That asymmetry mattered enormously. Theoretical models had often treated stellar eruptions as roughly uniform explosions driven outward equally in every direction. Eta Carinae showed something more complicated, shaped by rapid rotation, magnetic fields, and the gravitational influence of a nearby companion star. Massive stellar death suddenly appeared less orderly than expected. The Chandra X-ray Observatory added another layer. Its monitoring campaign across multiple orbital cycles produced one of the longest continuous X-ray studies ever conducted on a single stellar system. Researchers developed analytical techniques specifically to interpret the changing wind collision zone between the two stars. Those same methods are now applied to other massive binaries throughout the Milky Way. Even the chemistry proved surprising. Warm magnesium emission, discovered within previously unpredicted regions of the homunculus, revealed that the ejecta contained structures and temperature gradients older models had not anticipated. The nebula became not merely debris, but a laboratory for understanding how matter behaves after violent stellar eruptions. But Eta Carinae's influence extends beyond visible astronomy. Theoretical work modeling the binary interaction and mass loss history has contributed directly to modern understanding of compact object formation, including the black holes and neutron stars, now detected through gravitational wave observatories, such as LIGO. The mergers producing those signals begin with massive stars evolving through unstable stages, much like the ones observed here. The star has revised theory repeatedly. Nearly every periastron passage across the past 2 decades has forced at least one correction to the accepted model of the system. Predictions fail, observations disagree, and researchers return to the equations again. Eta Carinae has been correcting human assumptions on a repeating 5.5 4-year schedule. The way astronomers study unstable stars change too. Coordinated observation campaigns across X-ray, ultraviolet, infrared, radio, and optical wavelengths became standard partly because Eta Carinae demanded simultaneous monitoring from every instrument available. The methods pioneered here are now used throughout transient astronomy. And still, the defining event has not yet occurred. Everything learned so far came before the star's death, which means humanity may already possess the most complete preparation any civilization has ever had for witnessing a massive stellar collapse unfold in real time. Tonight, the light arriving from Eta Carinae began its journey toward Earth roughly 7,500 years ago. By human standards, that interval is almost impossible to hold clearly in the mind. Civilizations rise and vanish. Inside spans far shorter than that. When this light first left the star, humanity was still deep in the Neolithic world. Agriculture existed only in scattered regions. Early settlements in the Fertile Crescent were beginning to stabilize into permanent communities. Jericho had stood for only a few thousand years. Çatalhöyük still held inhabitants. Writing had not yet been invented. Mathematics, astronomy, and metallurgy remained centuries or millennia away from their mature forms. No one understood stars physically. The people alive beneath that ancient sky had no telescopes, no spectroscopy, no concept of galaxies or nuclear fusion. They did not know the universe contained distances measured in light years, or that light itself traveled at a finite speed. Yet, while they planted crops beside rivers and shaped stone tools by hand, photons were already crossing interstellar space toward a civilization not yet imagined. Those photons are reaching you now, but the same separation extends forward as well. Light leaving Eta Carinae at this moment will not arrive on Earth for another 7,500 years. The people who eventually receive it stand as far ahead of us as the builders of the first cities stand behind us. We cannot picture them clearly. Will human civilization still exist on Earth in recognizable form? Will telescopes even resemble the instruments we use today? Perhaps our descendants will observe the cosmos from settlements spread across multiple worlds. Perhaps knowledge of stellar evolution will seem elementary to them, the way Bronze Age astronomy seems elementary to us now. And still, they may inherit this question. If Eta Carinae has already exploded, if the light from that event is currently traveling silently through space, then the people who witness it belong to a future beyond our reach. They will possess discoveries not yet made, technologies not yet conceived, and archives containing centuries of accumulated observations from astronomers long dead, including ours. Every monitoring campaign, every spectrum, every X-ray record collected across the past decades becomes part of an inheritance moving forward through time. Researchers studying the system today understand this openly. The work continues despite knowing the definitive answer may arrive long after everyone currently alive is gone. But the effort still matters. Human knowledge has always depended on continuity between generations. Ancient skywatchers preserved observations for people they would never meet. Modern astronomers do the same now, maintaining instruments, refining theories, and recording changes in a star whose final act may belong entirely to the future. This is what the light delay truly means. We are separated from Eta Carinae not only by space, but by history itself. The answer to the question we have been asking may already exist, already be moving toward us, and already belong to descendants who will look back at our era as unimaginably distant. Eventually, the story of Eta Carinae stops being only about the star itself. The focus turns quietly toward us, toward the strange decision human beings have made to spend generations observing an event we cannot influence in any way. Nothing we do affects the outcome. The star will continue burning, shedding mass, destabilizing, and moving toward collapse regardless of whether anyone watches. No telescope alters the physics inside its core. No observation delays the explosion by even a fraction of a second. The forces operating there began long before humanity existed and will conclude, according to rules, entirely indifferent to human attention. But we watch anyway. That choice matters more than it first appears. The monitoring programs surrounding Eta Carinae are not defensive systems. They are not preparations for intervention. If the star exploded tonight, there would be nothing humanity could do except observe the light arriving across space. The effort exists for understanding alone. Across decades, governments funded observatories, engineers built detectors beneath mountains, researchers devoted careers to orbital cycles and spectral lines, and students inherited projects that may not conclude within their lifetimes. Thousands of hours of telescope time have been spent studying a phenomenon no one can accelerate, prevent, or fully predict. Pure witnessing. There is something ancient inside that impulse. Long before spectroscopy or X-ray astronomy existed, human beings tracked celestial patterns because watching the sky connected them to scales larger than individual lives. Ancient observers carved alignments into stone, marked planetary motions onto clay tablets, and recorded eclipses with careful precision despite possessing no practical power over them. Modern astronomy continues the same tradition with different tools. Instead of stone circles, we build interferometers and orbital observatories. Instead of naked eye observations, we collect neutrino detections and ultraviolet spectra. But the emotional structure underneath remains surprisingly similar. Human beings still look upward, searching for orientation within a universe vastly larger than themselves. Eta Carinae concentrates that feeling intensely. Researchers who entered the field during the 1980s understood immediately that they might never witness the star's final act. Senior astronomers told younger colleagues openly that the defining observation could arrive next year or after everyone currently alive had died. Careers were built anyway. The vigil continued. Graduate students studying the system now may someday become the senior scientists guiding future generations through another periastron passage decades from today. Data archives will expand, instruments will improve. The question will persist across people who never meet each other directly, yet remain connected through shared attention toward the same distant object. But no individual owns the answer. That may be the most important realization the star offers. Knowledge at this scale becomes cumulative and intergenerational. One group observes, another inherits, and another continues the work later still. The watch survives because the question itself matters enough to preserve. 7,500 light-years away, Eta Carinae continues evolving beyond our reach. Here on Earth, generation after generation has decided that simply bearing witness to that process is worthwhile. After spending so long beside a star defined by instability, it becomes easier to notice how unusual our own sun truly is, not because it is extreme, but because it is not. The Sun belongs to a category called G-type main sequence stars. In the language of stellar physics, that classification describes something remarkably ordinary. Its mass is average. Its surface temperature is average. Its luminosity is average. Across the Milky Way, there are countless stars broadly similar to it, and that quiet normality changed everything for Earth. For approximately 4.6 billion years, the Sun has maintained an astonishing level of stability. Its energy output fluctuates slightly through magnetic cycles, but not enough to destabilize planetary climate on catastrophic scales. Oceans remained liquid, atmospheres persisted. Chemistry unfolded gradually across immense stretches of time. Life required that patience. Complex biology cannot emerge in an environment constantly reset by violent radiation or repeated atmospheric collapse. Evolution depends on continuity. Cells divide, ecosystems adapt, and complexity accumulates slowly. A stable star provides the uninterrupted energy background that allows those fragile processes to continue for billions of years without interruption. Eta Carinae offers the opposite environment entirely. A planet orbiting that system at roughly Earth's distance would not survive its eruptive history. The ultraviolet radiation alone would be devastating. During the Great Eruption of 1843, the surrounding region was flooded with energy intense enough to strip atmospheres and irradiate planetary surfaces repeatedly. Any developing biosphere would face continuous disruption. The galaxy contains both kinds of stars simultaneously. Some stars burn quietly for billions of years, sustaining planetary systems through geological ages. Others consume their fuel rapidly, living brilliant and unstable lives that end almost as soon as they begin. Massive stars dominate their environments through violence, radiation, and explosive death. But those same violent stars create the materials life needs. The carbon inside living cells, the oxygen dissolved in oceans, the calcium within bones, and the iron carried through blood were forged inside massive stars that lived and died long before the sun formed. Without stars like Eta Carinae, the universe would remain chemically simple, filled mostly with hydrogen and helium. Yet, without stars like the sun, those elements would never organize into living systems. That contrast reveals something profound about our existence. We depend on two completely different stellar personalities operating across different stages of cosmic history. First came the massive stars, short-lived and unstable, enriching galaxies through eruption and collapse. Then came quieter stars capable of sustaining planetary stability for billions of years. We are products of both histories at once. The atoms composing Earth originated in violent stellar deaths, the conditions allowing those atoms to become oceans, forests, and conscious organisms depended on extraordinary calm afterward. Eta Carinae represents the first half of that story in its most dramatic form. In that sense, the star is both our ancestor and our opposite, the kind of object that made our existence possible, and the kind of object beside which our existence could never endure. Somewhere beneath the measurements, the orbital calculations, and the spectrographic data, another question lingers quietly beside Eta Carinae. Not a question about stellar physics, but about the strange fact that anything in the universe is capable of noticing stellar physics at all. The scale alone makes the situation feel improbable. The observable universe is approximately 13.8 billion years old. Current estimates suggest it contains around 2 trillion galaxies. Each galaxy holds hundreds of billions of stars, many forming, evolving, and dying continuously across distances so large that most events will never intersect with any conscious observer. The cosmos does not pause for witnesses. Stars collapse in darkness. Galaxies collide beyond detection. Black holes consume matter silently for billions of years. Physics proceeds according to its laws with complete indifference to whether any living thing is present to observe the process unfolding. Eta Carinae is no exception. The star has spent roughly 3 million years burning through its fuel, shedding mass, destabilizing, and reshaping its surrounding nebula without requiring attention from anything outside itself. It would continue doing so even if Earth had remained lifeless forever. But Earth did not remain lifeless. Across one small planet orbiting an ordinary star, chemistry eventually produced organisms capable of memory, language, mathematics, and curiosity. Those organisms learned that light carries information. They discovered gravity, nuclear fusion, and spectroscopy. They built detectors sensitive enough to measure particles arriving from collapsing stellar cores. Eventually, they found Eta Carinae. Now, observatories across Earth track the system continuously. Telescopes orbit above the atmosphere specifically to study its eruptions. Underground detectors wait for neutrinos announcing the death of a star thousands of light years away. Entire careers unfold around understanding a process that changes nothing about human survival directly. That fact is difficult to explain purely through utility. Carl Sagan once described conscious beings as a way for the cosmos to know itself. The phrase persists because it captures something scientific language alone struggles to express fully. Through consciousness, matter produced by ancient stars became capable of reflecting on the stars that produced it. The universe became observable from within. Whether that observation possesses meaning outside human experience is not a scientific question. Physics offers no evidence that the universe prefers to be witnessed. Eta Carinae will eventually collapse, explode, or fade regardless of human anticipation. The star has no awareness of the instruments pointed toward it. But our awareness remains significant to us. Every observation campaign, every monitored periastron passage, and every generation of astronomers continuing the vigil expresses something about the nature of intelligent life. Faced with an indifferent universe operating across scales beyond ordinary comprehension, we still choose to look carefully and understand what we can. That decision may be one of the clearest definitions of humanity ever produced. 7,500 light years away, a massive star continues following the laws of physics toward an ending already written into its structure. Here, on a small world orbiting a quiet star, conscious beings continue watching simply because knowing feels worthwhile. Inside servers, observatory vaults, and mirrored databases scattered across Earth sits a record of Eta Carinae stretching back through generations of human attention. Spectra, light curves, infrared maps, X-ray fluctuations, radio measurements, photographs separated by decades. Thousands upon thousands of observations collected patiently across orbital cycles that outlived entire research careers. The archive keeps growing. Hubble alone has monitored the system since 1990. Chandra added continuous X-ray coverage beginning in 1999. Ground-based observatories in Chile, Australia, South Africa, and elsewhere contributed nightly measurements through seasons when the southern sky carried Eta Carinae high overhead. No individual assembled this record completely. Graduate students process data that senior astronomers would later reinterpret. Engineers designed detectors whose observations became doctoral theses decades afterward. Instrument upgrades built upon anomalies discovered during earlier observing campaigns. Each generation inherited unfinished work from the one before. That inheritance matters. When the light from Eta Carinae's death eventually reaches Earth, the people who witness it directly may rely on knowledge accumulated by observers long gone. The calibration methods, comparison archives, and theoretical frameworks guiding future interpretation already exist because countless individuals chose to continue monitoring a star without certainty that the defining event would arrive during their lifetime. The neutrino systems waiting tonight embody that continuity clearly. The detectors operating beneath mountains and underground laboratories are descendants of the instruments that recorded the brief neutrino burst from supernova 1987A. Only 24 particles were detected then, yet those few detections permanently changed stellar astrophysics and justified building more sensitive observatories afterward. Each improvement extended the watch further. Science conducted across generations requires a particular relationship with time. Most human institutions prioritize immediate results, immediate rewards, immediate proof that effort produced value. But observational astronomy often asks something different. It asks people to contribute carefully to projects whose final significance may emerge centuries later. Eta Carinae exists almost perfectly within that tradition. The star will outlive every astronomer currently studying it. Future researchers, not yet born, will inherit the databases being assembled now. They may use instruments impossible for us to imagine, examining signals gathered long before their own era began. But the chain will remain unbroken. Meanwhile, Eta Carinae itself continues, without awareness of any witness at all. Deep inside the Carina Nebula, the star burns through nuclear fuel, sheds mass into surrounding space, and moves steadily toward whatever ending its internal physics permits. It does not know telescopes track its eruptions nightly. It does not know human beings built observatories specifically to follow its evolution. We are the only side aware of the relationship, and perhaps that awareness is enough. Tonight, the southern sky still contains the star exactly as generations before us saw it, unstable, luminous, partially hidden inside the expanding wreckage of earlier eruptions. Around the world, instruments continue recording its changing light automatically, patiently adding new measurements to an archive already vast beyond comprehension. The watch goes on. Whether the final signal arrives tomorrow or thousands of years from now, the light will encounter a civilization that prepared for it by paying attention carefully, continuously, and across generations.